Welcome to your guided tour of the most frequently seen and most important operators in an execution plan. Before we get started, I want to get a couple of things out of the way with regards to terminology and the way that I describe things in this video. First, I'm going to use the word reads, and it may not be the most accurate term, but I'm using it loosely speaking because when an operator like a clustered index scan or index seek goes to retrieve rows from storage, pulls them into memory, when that happens, it's accessing and retrieving and examining those rows. It does have to look at them at some point. So don't get too hung up on the fact that I'm using the word reads, which gets thrown around a lot in other SQL Server avenues. The second thing is, when I talk about what an index seek or a scan accesses, I'm ignoring the fact that there are filtered indexes. I'm talking about a typical non-clustered index that covers every row in a table, not just some of the rows the way a filtered index would. So just keep that in the back of your mind as well. With that said, let's move on to the first of our operators, the humble table scan. A table scan is an operator that you only see running against unordered structures or heaps. Things like tables without a clustered index, temp tables, or table variables. When is this a good thing? Not very often. There are times where it's okay to have a table scan. When you see it in the execution plan, you say, that's kind of what I expected, I'm good with that. Times like these include, if you have a smaller table, be it a physical table, temp table, table variable, whatever, if you're talking about hundreds of rows, that's fine. You can deal with that being a table scan in most cases. There are other times where table scans aren't so bad either. Say you have an ETL process that flushes and fills a table with no clustered index on it. It could be that that process will run a lot faster if you don't have a clustered index because things don't need to be ordered as they come in and out. It's important to point out in that case that you don't want to be deleting from that table. You want to just truncate it outright because a delete will have far more logging activity involved than a truncate will. Plus, heaps don't always behave well when it comes to releasing the disk space involved with the rows that were deleted. In any case, the scenarios in which using a table scan will be satisfactory are fairly limited, which brings me to the downside of things. And there are a lot of downsides to table scans. Obviously, having to search an entire table for whatever SQL Server is looking for is not an optimal strategy. Sometimes you can get away with it. If it's a small table, there's very little performance penalty between doing a table scan and a clustered index scan. But as the table gets bigger, this is going to get worse. Another problem that you can run into is that table scans, because they're coming from an unordered source, may result in the ordering of that source. There are times where predicates like exists will force data to be sorted in order for it to be compared. If you need that data to be compared, it may need to be sorted. If it needs to be sorted, then you probably would have been better off with a clustered index scan. Now let's take a look at what a table scan looks like in an actual execution plan. What we're looking at here is a good table scan, one that when we see it in an execution plan like this, we're happy with it. Let's say that we've got a table called Obi-Wans, and what we're going to do is create a table that just has an ID and a display name, and then we're going to make a table of all the people who have Obi-Wan in their name. Now, we don't know if they use spaces or dashes or nothing in between the Obi and the Wan part, so we're just going to say where the display name is like Obi and also happens to be like Wan, and let Stack Overflow figure out the rest. In our query down below, we'll select the ID and the display name, and then we'll also find out what is the total number of answers all of their posts have received. So we'll select from this temp table and join it to posts and go from there. When we look at the execution plan, it's really not that bad. The table scan itself is pretty cheap. It's got almost no cost to it because this is a very short list. If we look at the results, yeah, pretty short. There's only 8 people that fit. This table scan is inexpensive. The clustered index scan makes up most of the cost, where it goes through the posts and then gets matched up. There's only one sort operator, and the rest of the plan is relatively cheap. Now this could be improved upon with a non-clustered index. That missing index is actually on the post table. SQL Server wants to get rid of that clustered index scan. It's not so much concerned about our table scan. This is a pattern where if you need to reuse a small set of rows, the way we're doing here, then a temp table is a convenient way of doing it. And if it's small, you can get away with not having it sorted. You don't have to put a clustered index on your temp table or anything like that. Just roll with it the way it is. So in this case, we're doing exactly that, and it turned out fine. If we wanted to make this query faster, we're not going to accomplish that by swapping out the table scan. We're going to accomplish it by getting rid of the clustered index scan on the post table instead. Here is a bad table scan. Now I'm not showing you the plan right away because I actually got a worse plan when I ran this on a different server. So I'm going to show you the plan that I got from over there, and then I'll show you what we can do to make this even slightly better. So with this query, what I'm doing is selecting the post ID and title and a count of the number of comments. And I'm going to sort this record set by the number of comments in descending order. So the most popularly commented posts will be at the top. I've removed all of the indexes from DBO posts so that this will be a table scan on posts. We're joining it to the comments table by post ID. When we look at the plan, we can see that there's a lot of problems that come from using an unsorted data source. We're doing a table scan over here, which is pretty modest. It's really only 6% of the entire cost. But the problem is the havoc that it causes downstream. We've got a sort here on that table scan, and then we've got another sort on the clustered index scan so they can be put together in the merge join. Then they're sorted again, and then they're sorted one more time. And you may notice that all of these sort operators have the little yellow triangle warning you that something bad is happening. In each case, the operator has spilled over into tempdb, meaning there wasn't enough room in memory, so it had to write this stuff to disk. If we add up the cost of these sorts, 22, 21, 13, and 14, that's 70% of the cost of this query plan just spent on sorting and resorting things. Now to be fair, we're doing a group by and an order by, so yeah, some of that is going to come from the fact that we're doing those two operations. But there's still sorting that happens just because we had unordered data enter the mix. One more thing we'll look at here is the cost of this Big Daddy. $4,260. That's a really expensive query. So what we're going to do is to see if we can improve upon this, we're going to make just one simple change. We're going to take this table scan and make it a clustered index scan. All we're going to do is make sure that the data that comes from our post table is now sorted in storage. It doesn't even matter if it's the right order, as long as it's an order. If we go back to our original query here, and we reveal the plan, this is what it looks like when we add a clustered index. Now we've still got a clustered index scan over here, like we had before on the comments, but now it makes up a much larger share, 48% of the entire query cost. Our clustered index scan on the post table replaces the table scan, and its cost also went up. But that's because these are relative to the rest of the plan, and look at that. There's only one sort operator now, and that sort operator takes place after all of our data are put together. So this is, if we hover over, putting things in descending order. This is the order by count. So the only sort that we're encountering here has to do with the order by that we put in. There's no sort taking place on either of the two clustered index scans anymore. So you see how introducing ordered data from a clustered index can make a big difference in the query plan versus having unordered data. One last piece of proof, if we look at the select statement, now instead of the $4,260 subtree cost, we're down to $1,470. Make no mistake, that still stinks. It's just that it's nowhere near as bad as it was before. So this is a particularly atrocious table scan, not just for the fact that it has some expense incurred, but also everything that happens downstream of the table scan is bad too, because the table scan was there. A clustered index scan is just like a table scan, only the table scan is unordered, the clustered index scan is ordered. Of course, the order here being the order that the clustered index goes in. The columns that are defined in that index define how it's ordered in storage. A clustered index scan isn't always the best solution. In fact, it usually isn't, but it is a useful operator in certain situations. Situations where you say, clustered index scan, I'm fine with that. For example, when your table is smaller, just like with the table scan, you're probably going to be okay with a clustered index scan, something that covers hundreds or maybe even thousands of rows. It's probably going to be all right. Also, when you have a materialized indexed view, materialized simply means that you define a clustered index for that view, or if you've got a clustered index on a temp table or table variable. You can actually have a clustered index on a view, a temp table, or a table variable, although the rules for defining those kind of vary. Other times where it's good to have a clustered index is when there's a low relative cost. If you see that in your query plan you've got a clustered index scan that accounts for 4% of the total cost, it's probably not a big deal. You can shrug and move on to the more expensive operators. Remember in a previous video how we talked about scans, seeks, and sargability? This is one of those times where if you have a non-sargable statement, you can expect to be sent back to a scan as opposed to getting any kind of a seek out of it. This may be a clustered index scan or a non-clustered index scan, just depends on how your indexes are built. But it's the kind of thing where if you're getting the clustered index scan, it's really up to you whether to determine if that's going to be worth trying to get a regular non-clustered index scan versus a clustered index scan. One more instance where it's acceptable or okay to have a clustered index scan is if you're seeing it against lesser used columns. Say we don't have a lot of indexes on this table and it's not worth indexing just to make this one low-cost clustered index scan into any kind of an index scan or index seek. If that's the case, sometimes you just roll with it and say it's good enough. Again, it depends on the relative cost of that particular operator. Which brings me to, when is it a bad thing to see a clustered index scan? There are 3 occasions where maybe we should look to improve upon the situation. If you see a clustered index scan against a table that has a whole lot of rows, millions of rows, then it could be that you could improve upon the clustered index scan even if it's not an extremely high cost operator. There's still room to narrow things down a little bit, potentially. Another time where you don't want to see a clustered index scan is if you have room to index, say you've only got 1 or 2 non-clustered indexes and there's no reason you couldn't add more to cover this, and it's part of an execution plan that's tied to a very problematic or expensive query. If that's the case, then yeah, seek to get, good pun there, seek to get rid of the clustered index scan or replace it at least with some sort of index seek. And then the final time where you would want to pay attention to this is, again, if it's a high relative cost. If you've got a clustered index scan that's brutal in terms of the percentage of the cost of the plan, 50% or more, then you may want to look at reducing that by changing things around, adding an index that will get rid of the clustered index scan. Now let's take a look at a clustered index scan in a real-life execution plan. All right, so let's take a look at a couple of clustered index scans. The first one we'll look at is a good clustered index scan. So we've got select ID and type from DBO post types, where the type is like, and then somewhere in that string, the word answer, or at least the 6 characters that make up the word answer. Why is this a good clustered index scan? For the simple fact that it's cheap. This is a teeny tiny table, and you look and it only had to read 2 rows and only returned 1 actual row, and the costs are almost 0. So this is a clustered index scan we really don't care about, and obviously we can't do much to improve upon it because it's just so cheap to begin with. This is the kind of query that if I see it in someone's environment, and it's running thousands of times per minute, then I'll ask, okay, can this be cached or made part of the app somehow, as opposed to asking SQL Server this question repeatedly. But if it's not avoidable, or if it's not part of an app, if it's just something that I see running from time to time, I'm not going to worry about this at all. It's so cheap, just don't sweat it. Here is a bad clustered index scan, one that if I were to see it, I would want to try to improve. We've got select ID from DBO posts, where title is like, and then problem is somewhere in the title. It can be beginning and middle, doesn't matter. But we're looking for the word problem in the title. Because this statement isn't sargable, it's the wildcard operator at the front of the word problem that makes this not sargable, we know that we're going to be stuck with a scan. It's going to be a clustered index scan or a non-clustered index scan, but a scan just the same. Why do we want to avoid this particular clustered index scan? It's all about the cost. If we look at the cost of this plan, the estimated I/O cost for the clustered index scan is $461. That's pretty steep. The problem here is that because it's a clustered index scan on posts, we're bringing all the other stuff that comes with the post table into the fold. And if we look at what's in the post table, we see that there's stuff like body, which is end text. And we've got title, which is nvarchar 250, and tags, nvarchar 150. We've got some pretty wide fields in there that we really don't want to have to deal with if all we're looking for is the ID and we're just trying to look things up by the title. So the way that we'll go around this is to create an index that will satisfy this particular query and give us a way around that clustered index. All right, so our index is created. Let's go back and run this again. What should happen is SQL Server should pick up on the fact that we've got a much better index to use and avoid the clustered index. And there we go. Now this is still going to be expensive relative to the rest of the plan as far as the index scan goes, because there's just not much else going on there. But if we look at the cost now, rather than having the I/O cost be $461, we've managed to shave a whole lot of I/O off of this by just leaving unrelated columns out of the equation. So now our I/O cost is 69.6. That is way better than the 461 we were confronted with earlier. So the short story here is that because the clustered index involves some very wide columns, we want to cut those out of the equation and just have an index that is relevant to what we're looking for. A clustered index seek is kind of like an index scan, only in the sense that they go in two different directions. What I mean by that is that the index scan contains a subset of columns, not every column. A clustered index seek contains all the columns, but only a subset of rows, not every row. I don't know what I was doing with my hands just then, but if you just listen to what I'm saying, that's probably going to be good enough. In any case, a clustered index seek will only target specific rows as it looks for whatever it's trying to match up with. This is a good thing because now we're not hitting every row in the table. This is good to see for things like small tables, lookup or reference tables, for example, like post types. If the table is narrow, then it means that we're getting the benefit of seeking out only certain rows, but we're also not bringing back a whole bunch of stuff that comes with each row. Sometimes it's good to have a clustered index seek. For example, when you have limited indexing opportunities. Either you've got a lot of indexes that you've created and you want to keep them all, and the table is so big that you don't want to add another index to it. Or maybe you've got a vendor app where you're not even allowed to touch the indexes. And you look at the execution plan and say, I could try to fix this some other way other than through creating a new index, but I'm just going to let this one go. Here goes again. If the operator has a high relative cost to the rest of the plan, then yeah, you probably want to do something about it. Other times where a clustered index seek is not such a good thing is when you have a wide table. Because we're doing a clustered index seek, even though we're able to target a subset of rows, we still have to get every column. And for a table like posts, for example, there are comments, and that comment field is pretty wide. If we don't have to pull that into memory, why should we? Let's try to get a non-clustered index that doesn't involve the comments field to satisfy that instead. Now let's take a look at a real-life example of a clustered index seek in an execution plan. Here's an example of a good clustered index seek. We're selecting some IDs from posts, and we want to join the post types. We're just kind of bringing it along for the ride here. Ignore the fact that it's sort of redundant in this case. But we're searching where post type ID is 1, and creation date is 2013, September 6. If we look at the execution plan, the clustered index seek is taking place on the post types table down here. This is taking up almost no cost whatsoever compared to the rest of the plan. And if we hover over it, it's actually reading just one row. So this is one of those situations where the table is small enough that we really don't care if it's having to do a clustered index seek. We're not going to try to make that better with a straight up index seek. The table is so small that it really won't matter. Now let's take a look at a bad clustered index seek. Here's a clustered index seek that I don't personally like, but it's not as though we absolutely have to replace it. Again, we're hitting the post table, and the post table is kind of wide. The good news is here, we're not selecting every single row. We're doing a seek because we've got the clustering key in our where clause. If we look at what this is doing, it's bringing back 500,000 rows, which is not the most high cardinality seek we can imagine, but just the same, it's selecting only certain rows, and it's seeking to find them when it looks for them in storage. Looking at the estimated I/O cost, it's really not that bad. It's 14 for 500,000 rows. Okay, we can probably live with that. Okay, there are a few reasons why we might want to improve upon this seek, even though it doesn't appear to be much of a backbreaker performance-wise. The first reason is we've only got a couple of columns involved here, ID and title. Remember that the post table is pretty wide and it's got a lot of other stuff that comes along for the ride, whether you want it to or not whenever you hit the clustered index. The other reason why this may be something we want to improve upon, despite its seemingly low cost, is this might be the kind of query that runs a lot. It could be a very heavy use query, and although the cost, 14, doesn't seem all that large, it may be the kind of thing that racks up a lot of resource consumption volume-wise. So in that sense, we could try to make this better by turning this clustered index seek into a non-clustered index seek. Let's do that. We'll create an index just on post title and the ID. All right, our index is done. So what we'll do is we'll run this again and recompile, and it should do an index seek on the index we just created. All right, there's our 500,000 rows, and sure enough, it did an index seek. I remember the original cost was 14. Let's see what it is now. Okay, so it's down to about 2.5. This is significant for a couple of reasons. One, we just made a query about 7 times faster. But the other thing is, if you have a cost threshold for parallelism that ends up being the dividing line between the clustered index seek and the index seek, you may be able to sort of reclaim some CPU by not having this query go parallel. So in that sense, we've taken a bad clustered index seek and turned it into a good index seek. Index scans are a lot like clustered index scans. They access every row in the index. However, they don't access every column because an index, a non-clustered index that is made up of a subset of the columns in the table. So by definition, you can expect that an index scan will be smaller and use up less resources to go through than a clustered index scan would. Just to clarify at this point, an index scan and an index seek, when you see them in an execution plan, refer to the non-clustered indexes, not to the clustered indexes. Rather than specifically say non-clustered index scan, the execution plan will just shorten it. The index scan will traverse through the index in order of whatever that index's order has been defined to be. So if it's ordered by post type ID, last editor, user ID, whatever, that's the order in which the scan will take place. There are good and bad times to see an index scan. One of the good times that you want to see it is when you have a non-sargable statement, something where it's unable to seek out what it's looking for because it's just not part of the ordered structure. Kind of like the example where we looked at like Obi-Wan, where there could be characters in front and characters behind. An index scan is about the best we can hope for there. Being that an index is a subset of all the columns that make up the clustered index, we can kind of deduce that it would be better to have a smaller footprint and go through the index than it would the clustered index. There are times where an index scan is a bad thing. One of the times that we should be unhappy to see an index scan is if the index in question has a really wide column in it. Say, for example, an nvarchar 4000 or nvarchar max or something really large, XML, image, whatever. If we can avoid hitting that column, then maybe it's better off that we create a different index, even if it's a different index that we scan through. Because what we want to do is avoid taking up a bunch of resources by pulling in large columns into memory and pulling large columns from disk. Remember, the name of the game here is to make your footprint as small as possible. So in that instance, we may be better off creating another index, even if we're stuck getting an index scan from that new index. It may just be a better option overall. Another time where it's not really going to be satisfactory to have an index scan is when that index scan has a high relative cost to the rest of the execution plan. We look at execution plans, see that the index scan is 50, 70, 90% of the plan. That tells us that there's room for improvement there. Just like with our other query tuning efforts, when we see an operator that's taking up most of the execution plan's cost, we want to find out why and see what we can do about it. So now let's take a look at an index scan in a real-life execution plan. Here's a situation where we have what we would consider to be a good index scan, one that we would see in an execution plan and say we're happy with that. We've created an index to make sure that this actually happens on an index to get the scan, obviously. And we're selecting the ID and display name from users where the left 3 characters of the display name are OBI. Now, it seems kind of dumb that SQL Server can't make this a sargable statement. But if you think about it, it has to bring in the display name and then do some thinking about it, and that breaks the sargability. In any case, we're stuck with a scan because of the where clause we've chosen. The reason why this doesn't really bother me too much is that this index scan is fairly lightweight. It's having to read through all 2.3 million rows. That's unavoidable again with our statement here. But at least the cost is fairly low. It's down to like 7. And even though it takes up a fair amount of the relative cost to the rest of the plan, it's still hitting an index that only has the ID and display name. I don't have anyone's about me being brought along for the ride here. So it's fairly straightforward here. This is an acceptable index scan because there's not much more we can do to make this more lightweight. Let's take a look at where that's not the case in a bad index scan. This is an example of a bad index scan. I've created an index called IXBigDisplayName because it's the display name, but now we've brought the About Me column along for the ride. The About Me column, let's find it here, is nvarchar max. Uh-oh. That's going to take up a lot more space, especially if people are really vigilant about filling out detailed biographies in their user profile. Let's hope that that's not too damaging in this case. So we run this again, we look at the index scan that results, and for one thing, it's now big enough to go parallel. That's not a good sign. And the estimated I/O cost is 13.85. That's significantly larger than when we did our good scan and we got 7.1. So basically, by choosing the wrong index, we've doubled the I/O cost associated with this query. It's important to be able to recognize this because SQL Server won't always make the best choice when it comes to what index to hit. Or it could be an indicator that an index you thought was there has been disabled or deleted entirely. So it's important that when you troubleshoot execution plans and you look for index scans, that you make sure that they're hitting the best index they can. And the last of the 5 major data retrieval row set building operators is the index seek. Under most circumstances, this is the operator that you want to see because it will be the most efficient. It's the most efficient usually because it accesses just a subset of columns, that is the columns in the index, not the clustered index, and a subset of rows, meaning if it's doing a seek, it's not touching every row. So it has the smallest footprint of the 5 that we talked about. So of the table scan, clustered index seek, index scan, and index seek is usually going to be your best choice. One thing that's kind of curious about the index seek is that it's usually good even if it has a high relative cost. Because it could be that at that point there are no other operators in your execution plan that are going to be expensive by nature, and that the data retrieval part is just going to be the most expensive part no matter what. In that case, it's actually okay to have a high cost index seek. There are, however, times where it's not so good to have an index seek. One such time is when you have the wrong index being sought on or seeked on, or whatever the word is for that. If you are looking at an index that involves, again, like a huge comments field or something, and you want to avoid that column being part of the equation, then you may be better off creating a new index or having to hint to an existing index that SQL Server just isn't paying attention to. Because again, you want your footprint to be as small as possible here. And it could be that the index seek that's taking place is happening on an index that is really not a good choice overall. There's one other occasion too where having an index seek is not a good thing. In fact, it may even be beaten by a clustered index scan. That's right. It may be beaten by a clustered index scan. Let's say we've got a table. So we've got columns and we've got rows. Of the 4 operations we talked about, there's the clustered index, non-clustered index, scan versus seek. We'll go through all 4 now. The clustered index scan touches every column and every row. A clustered index seek touches certain rows, but every column. An index scan touches certain columns, but every row. And an index seek is sort of the best of both worlds between the clustered index seek and the index scan, in that it only touches a subset of columns and a subset of rows. So how in the world can an execution plan be worse off with an index seek, which only touches pieces here and there, versus a clustered index scan? Seems kind of crazy, doesn't it? Well, like everything where there's a rule, there's bound to be an exception. So let's check out an execution plan now that actually shows you may be better off with a clustered index scan than you would an index seek. Here we have a bad index seek. It's not so much that the index seek is to blame for it being a big problem query. It's the kind of stuff that gets partnered with the index seek in this case. In order for us to measure the impact of having a bad index seek and be able to say, yeah, a clustered index scan will do better than an index seek, we have to use a different metric than what we've been using. We've been looking at estimated I/O cost to this point. Now we're going to switch over to CPU time. In order to do that, we'll set statistics time on, and it will tell us the CPU time and elapsed time. Now what we're going to do is run this query where we select post type ID from posts where last editor user ID is some parameterized value. This last editor user ID of 44 only returns 5 rows. And if we look at the CPU time involved, it's practically instant. Here's our execution plan, and in this case, it's a good one. We want an index seek and a key lookup and nested loops because these are all small, tiny operators, and we're only talking about 5 rows. We want to see really skinny arrows like these guys here whenever we see index seeks and key lookups paired together with nested loops. If we run this again against 0, or with a parameter value of 0, the 0 kind of represents nobody in the Stack Overflow database. There's no record in the users table that maps to that 0. So if we run this exact same statement, only we give that parameter value 0, we're going to get 10.7 million rows back. But if we get that many rows back, do we still want the index seek and the key lookup? Let's find out. Okay, so our query's done. Let's take a look at the execution plan. Okay, this is not good. We've got the index seek and key lookup, but we've got some really fat arrows going from those two operators into the nested loops. If we look at the key lookup, we'll see that the number of executions was 10.7 million. Now this doesn't mean that SQL Server went to storage to get the clustered index and pulled it into memory 10.7 million times. What it does mean is that SQL Server pulled the clustered index into memory and then referenced it 10.7 million separate times. So it's not bad, but it's still bad. This is only half the story, however, because I teased earlier that a clustered index scan can beat an index seek. We've seen now that the index seek is not good. Let's go get an actual number for that. All right, exactly 38 seconds. So don't pay attention to the elapsed time here, this 85 seconds. A lot of that was just time spent writing out that 10.7 million rows into Management Studio. That's sort of out of our hands, so let's just focus in on the CPU time, something that we can much more directly control. Let's find out how we can beat this now using a clustered index scan. First thing we'll do is free the procedure cache to make sure that that plan is blown out. Now what we'll do is run this query again, and this time when it formulates a plan, hopefully what will happen is it will use a clustered index scan or some other method that is more efficient than the plan it had been reusing. So let's run that and find out if we can get lucky. All right, so we've run this query. Let's see if we got a better plan. Oh, we didn't. We got the same plan as before. And it still took a long time. All right, so that won't be enough. It's clear that even though there's a clustered index scan that SQL Server could choose for this, it's not doing that. It's making a bad choice. So what we're going to do is, because this is a development environment, I'm not going to disable an index. I'm not going to hint that it use a different index. I'm just going to drop that index that it's using. Make sure that's the same one. IX last editor user ID. Yep, there it is right there. So I'll drop that. And now the time to beat is 38 seconds flat. Here goes. All right, so in real time, it finished in 44 seconds. Let's take a look at our execution plan. All right, so there is a clustered index scan here. And make no mistake, it's expensive from an I/O perspective. And if we were to create this recommended index, that would help quite a bit, 99.99%, in fact, according to SQL Server's guess. But what really matters? Did our clustered index scan beat the index seek? It sure did, 12 seconds. So this ran roughly 3 times faster than the index seek. And again, it's not so much the index seek's fault, it's the fact that it got paired with a key lookup and then nested loop join. Let's see if we can now go back and make this a happy query by taking the missing index and implementing it. So I'm just going to call this the last editor user ID and then include post type ID. We'll create this index, And when it's done, we'll go back and run our query again and see how much faster we can get than the 12 seconds we got from the clustered index scan. All right, our index is done. Let's hop back over and we'll free the procedure cache again. And now we'll run this one more time. The mark to beat is, oh, it's gone already. The mark to beat is 12 seconds. Okay, that took 36 seconds of real time, but it only took 4 seconds of CPU time. There are 2 lessons here. The first is that not all index seeks are created equal. It could be that you will get the wrong index seek. In this case, we had one that worked really well and then one that didn't do so hot. So when you see an index seek in your execution plan, you do have to cast a bit of a critical eye on it to see if it's really put in the best situation. Where the index seek failed us in this case was where it was paired with small-timey operators like the key lookup and the nested loops, operators that totally buckle under the weight of having to do 10.7 million operations. The second takeaway here is that SQL Server will do something called parameter sniffing, where it will reuse a plan and reuse the operators that came with that original compilation. That compilation is based on certain assumptions about the number of rows you're going to get back. In this case, it made an assumption that small-time operators were appropriate for the number of rows that we were going to get back. And that was true at the outset. We only got 5 rows back. But when that plan was reused for 10.7 million rows, those small-time operators buckled under the weight. This concludes part 1 of our tour through all the operators that you'll see in an execution plan. Coming up, we'll look at operators like joins and the key lookup. Stay tuned, we'll return after these messages.